In the beginning of Chapter 15, we're going to take a look at probability histograms. And what a probability histogram is basically a pictorial representation of the likelihood of each possible outcome in a chance process. That's a lot of words. What do I mean? Well, I guess the best way to demonstrate it is with an example. Let's build a probability histogram together. In class, you're going to be doing it by hand, but we'll take a little bit of a shortcut and use the data program right now. So let's build a probability histogram for flipping a coin. So on a coin, I have my count values, or I have my counts and my values. So what it means by count is actually the number of that type of ticket. And what they mean by value is the number written on the ticket. So in my probability histogram for a coin, I'm going to have one side of the coin that says, well, what are we measuring, Carly? Should we measure heads or tails?
Let's do heads.
So we're making a probability histogram of flipping a coin and getting heads. So I have one side of the coin that has a 1 on it, because each time I flip a coin and get a head, I'm going to count 1. We're summing up that total. And then the flip side of that coin, no pun intended, is the tail side, which we're going to count as 0 because it's not what we're looking for. So here we are, one side of the coin that says 1, one side of the coin that says 0. Let's take a look at our box. Our box is demonstrating that both getting a head and getting a tail are equally likely chances. And when you look at this box, it shows that the average of our box is 0.5, which is true. 1 plus 0 divided by 2 is 0.5. And the standard deviation of this coin is 0.5. These are numbers we've come familiar with as we've been working with these coins. So let's build a probability histogram just based on, let's just say, one flip of the coin. So let's see if we were going to make a histogram of the sums. So over here we have the contents of our box, basically on one draw, one flip of the coin. Well, let's build a probability histogram based on 2 draws, meaning we flip the coin twice. What are the possible outcomes if we flip a coin twice and we're tallying up the number of heads? Well, we could lose altogether and get 0 out of 2 flips being heads. We could get one of our flips ending up being a head, or we could go really big and win them all and get 2 total heads. So, and the most likely option we're able to see is that 1 head, 1 tail, and that's the most every bar being the tallest. And as you'll notice, with every draw that we pull from the box, our probability histogram continues to grow and grow and grow, ranging from 0 to the greatest number of heads that we possibly could have. But we'll notice that the bars are the highest around that center. So this is starting to look a little. What is this starting to resemble, Carly?
It looks familiar. It kind of looks like the normal curve.
I'd say
like
so.
That bell-shaped curve.
Yeah, I agree. So let's see if we flip it more, if it's going to look, wow, yeah, it's starting to look more and more like the normal curve. We're starting to go from these very choppy edges into something a little bit more rounded. And as you see even more, 31 draws, let's keep on going, 36 draws. These choppy edges are starting to straighten out to become that beautiful normal curve that we've become so familiar with in the past few lectures. And there we are, we're getting to 100 draws. Look at that. So if we were to flip a coin 100 draws, we have these probabilities ranging basically down to close to 30, all the way up to close to 70
I have a question.
Yes.
But couldn't you get 0? If you flipped it 100 times, you could get 0 heads theoretically, or 100 heads, but how come it's cut off there?
Theoretically, we could get 0 heads. But what these probability histograms lay out for us is the likelihood of each event occurring. So when we flip a coin 100 times, the most likely event is going to be what, Carly?
50.
Exactly. That's where the bars are the greatest, right in the center.
Yeah.
But what would the likelihood of flipping a coin 100 times and getting 0 heads, getting all tails?
I guess that would be very small. So maybe there is a bar, you just can't see it because it's so small. It could happen, but the probability of it happening is so small that you can't even see it on the graph.
That likelihood is so small it's considered negligible, basically. That the chance of that occurring is really, really tiny.
Oh, so it goes on from 0 to 100. It's just so tiny you can't see see it.
Exactly. So instead of wasting all that space on these graphs,
Yeah,
we just want to really focus on the most likely events. And the most likely events are going to be ranging, from that 40 to 60 range, basically, with the highest likelihood around that 50. And what I find fascinating about this 50 in the middle, Carly, is 50 for 100 draws would be our expected value, right?
Right.
So we're able to see that for each of these histograms, the expected value seems to be right smack dab in the middle. So if I flipped a coin 100 times, we would expect to see 50 in the middle. If we were to flip a coin 1,000 times, we would probably see 500 in the middle. So that's what these probability histograms lay out, the likelihood of each possible outcome for each draw from that box. Yes?
I have another question. It says SD equals 5, but is that really the SE, what we've been calling the SE?
Exactly right. This actually, the standard error of our box would be 5 for this case. That's exactly right. So when you're reading these, you can consider this to be your average of the box, the average of 500 draws, and the standard error of 500 draws up on the top. So it kind of saves you a little bit of extra math you have to do. So the beauty of this, why is this useful to us? The beauty of this is we're going to see in class how tedious it is to build these probability histograms for each individual problem. Flipping a coin 100 times would take hours if we were to do this by hand. And what we're able to demonstrate is that these boxes look so much like the normal curve with enough draws that we're actually able to substitute the normal curve for determining the probability of certain events occurring. Now Carly, what do you think? If we had a really lopsided box, this one's very even. 2 numbers right next to each other with equal probability. Would we see this normal curve occurring if we had a really lopsided box?
I don't know, can we try it out?
Let's test it out. Let's go back to choosing our box. What do you say? What's a really lopsided box?
Let's have 17 be one of the values.
Sure.
That's a big number.
Instead of the 1 and 0, which are right next to each other, let's make it 1 and 17.
Yeah, and then let's make the counts difference. Instead of 1 and 1, we could have 50 and 10.
Yeah, sure, that works.
Wow, that sounds so strange. Which one do you want me to do 50 and which one do you want me to do 10?
Do 51s and 10 17s.
That's a strange box.
That is a strange box. So let's take a look at that. Wow, lopsided, right? We see a huge, the contents of the box are mainly filled with 1s and just a few of these 17s. So let's choose from our box and build our probability histograms for each number of draws.
Whoops.
There we go. So we're going to hit more and have these draws start building up. This does not look like the normal curve. This does not look like the normal curve, but wait! Look at that!
That one kind of does.
The edges are starting to kind of curve out. We're starting to see the center build up and the sides go out. And oh my gosh, when we're getting 60, closer to 70 draws, we're seeing this normal curve develop. So the take-home message is, no matter the contents of the box, whether it's so even or lopsided, like in this case, if you pick enough draws from that box, it will eventually, our probability histogram, will eventually develop into a smooth, normal curve. Now Carly, which do you think we would have to have more draws of in order to reach that normal status?
So probably the lopsided box, because it took us more times of starting over and getting different draws to get it to look like this nice normal curve.
I agree. If we have a nice, normal, even box, it'll probably take relatively few draws to hit that normal curve status. While with a really lopsided box, we're going to have to keep pulling and pulling and pulling, and here we are almost at, closer to 300, and now it's really starting to get normal. So the more lopsided your box, the more tries. Now how can we use this in normal approximations? Well, let's find out.
So now we have our normal curve. So if we're flipping a coin 100 times, how many heads would we expect to get?
50.
50,
Yeah.
right.
Because there's a 50-50 chance of getting a head or a tail.
Exactly. So our middle value is going to be 50. But you guys have seen the normal curve before. Do we usually have a 50 in the middle?
No.
No. What do we have?
0.
Yeah.
0,
Z
right.
equals 0 is always in the middle.
Yes, z equals 0. So now we know we have 0, and then we have 1 on this side, and -1 on this side. That's our classic normal curve that we've seen. But we're interested in the probability of getting more than 60 heads in 100 draws. So where am I going to put that 60? We know that 60 is 10 more than 50, but how do I know where to draw it on this normal curve?
Well, I guess maybe we should get out of heads as our unit and go into z-scores, standard units.
Right, exactly. So what's the formula for finding a z-score? We've done this in previous chapters.
Well, z is equal to the value minus the average over the standard deviation.
Minus the average over the standard deviation. Right. But now, instead of being given the average and the standard deviation, we're given the expected value of the sum and the standard error of the sum. Because we're looking at flipping a coin 100 times and we would expect to get 50 heads. So instead of using value minus average over standard deviation, now we're going to actually have a kind of new formula for the z-score that uses this expected value of the sum and the standard error of the sum. So all we're going to do is replace the average with the expected value. So we have value minus the expected value of the sum, and then replace the standard deviation with the standard error of the sum.
So this is what we're going to use to convert to z-scores now.
Exactly. So now we have 60 as our value. We know that. So if we're converting it to a z-score, we just have 60 minus the expected value of the sum, which we're given is 50, divided by the standard error of the sum, which is 5. So what do I get for my z-score?
2.
Perfect, 2.
2, exactly. So now we know where to draw that 60 on a normal curve because it's in the form of a z-score. So we have 0, 1, 2 would be somewhere over here. So this would be 60.
Oh, so the 60 represents two standard errors away from the average.
Exactly, away from the expected value.
Away from the expected value. It's hard to go
Yeah.
out of that lingo.
Exactly.
So 60 is two standard errors away from our expected value. So that's how we would plot it on the normal curve.
Right. So now, let's look again. What are we being asked? The probability of getting more than 60 heads. So if I wanted to shade that probability on this normal curve, would I shade to the right or to the left?
Well, here's 60. We want more than 60, so to the right.
Right, so that probability is everything to the right. So now, where do we go from here? What do we do if we want to find this probability and we know we have a z-score of 2?
Well, we have a lot of missing information, like the middle area, for instance. We should probably start
Right.
filling in this normal curve with those probabilities.
Exactly. So let's just get our middle area first.
Oh,
So
I
that's-
know that one. 2 and -2?
Yes,
95.
that's right.
Yep. So our middle area is 95. And now we just want this tail.
Okay.
So if our middle area is 95, what is this tail and this tail added together?
Together, we're missing 5%.
Exactly. So then one of the tails would just be 2.5%.
Oh, so half of what we had before.
Right. And the other tail would also be 2.5%.
Great. So this all adds up to 100, 2.5, 95, and 2.5. So the whole curve is filled out. Now we just have to read it, right?
Right, exactly. So we want this shaded area, which we actually have already marked right here, as 2.5%. So the answer to this question of what is the probability of getting more than 60 heads in 100 draws is exactly that, 2.5%.
That's a lot smaller than I would have guessed. 60 doesn't seem that far off
Right.
from 50 on the normal, or on a flipping a coin. That's amazing. So we were actually able to use the normal curve, tying in expected value, standard error, z-scores, everything we've been working for with descriptive statistics, and we've been actually able to compile it all for these chance processes, to actually use it to approximate the likelihood of an event occurring. That's pretty exciting stuff.
Yeah, that's
Pretty
pretty
cool.
cool.